Greetings. Since it is already 5, let me start our 12th live session on this course, Semiconductor Devices and Circuits. And the course is being taught by Professor Sanjeev Samadan. And we regularly solve the assignment problems in these live sessions. So today we'll be starting with the problem 6. Uh, We had left the previous class with the question number 7, but we had skipped the sixth problem because we said that we will be doing this. It will be a bit time consuming. We will do this in next class so that the theoretical question that was there, it could be covered. So this question over here, it states that this is regarding the MOSFET that we have been studying till now. It says that we have some n-channel MOSFET and the channel width in this case is been given to be equal to 30 micrometer and the channel length is given to be equal to 1 micrometer. Similarly, we have been provided the oxide capacitance which is 69 nanofarad per centimeter square, and we have been told that this MOSFET is in non-saturation region since we have applied a small amount of VDS, and for that amount of VDS, that is 0.07, this MOSFET is biased for 2 VGS, 2 gate to source voltages. For one of the VGS, that is 1.5 volts, the MOSFET over here is uh, having the drain current to be equal to 25 microamperes, and for 2.5 volts of gate to source voltage, the MOSFET is having the drain current of 65 microamperes. So this is the question, and this is some problem regarding the extraction, how we can extract the parameters. And in here we have been told to extract the mobility. So okay, so let's begin with this problem. We know that this MOSFET, we have been told that it is in non-saturation region. So it means that this MOSFET is in linear region since this MOSFET is having small VDS. Wait a second. Okay, so since this VDS is small, let us write down the MOSFET equation, the drain current equation for this MOSFET in the linear region. Let us write down for small VDS, the MOSFET is in linear region. This MOSFET is in linear region. So the drain current equation will simply be equal to ID is equal to mu n, where this mu n is the mobility, mu n C ox, W by L VGS minus VTH, where this VTH is the threshold voltage, and this has to be multiplied by this drain to source voltage. This is the drain current that we will be getting uh, for two different biases. In here we have two VGS. One VGS is 1.5 volts, and for that ID is equal to 25 microamperes, and other VGS, which is VGS2, which is 2.5 volts, and for that the ID is given to be equal to 65 microamperes. Now let us try to extract now the uh, mobility for these transistors. for these MOSFETs. So the first one was we had been given the ID to be equal to 25 microamperes. So let me write down it. 25 microamperes is the current, and mu n is the mobility. Oxide capacitance is 69 nanofarad per centimeter square. So it's 69 into 10 raised power minus 9, and W by L is, we have been given the width to be equal to 30 and the length is 1 micrometer. So it would mean we will be having 30 is to 1 as W by L. So VGS is simply in this case 1.5 volts. So it is 1.5 minus, sorry, so it is 1, wait a second. Okay, I wrote 15. It is 1.5 minus the threshold voltage, which is VTH, times the VDS. VDS is quite small. It is 0.07. So it is 0.07. Okay, in here we are having two variables, that is mu n and the threshold voltage. So we need to have another equation, and that's why we have been given another bias condition, that is for VGS2. And for VGS2 we have been told that the current is 65 microamperes. So it is 65 into 10 raised power minus 6. Rest of the things will remain same for this except the bias. So it is 69 into 10 to the power of minus, and this will be simply 30 by 1, and this bias is 2.5 minus VTH into 0.07. Now uh, we can do the simple manipulation. We can just subtract the two equations. Let me write down this as 1 and this as 2. Let us subtract equation 1 from equation 2. So it will simply mean I will be subtracting 65 minus 25 into 10 to the power of minus 6. This will be mu n C ox 2.5 minus of VTH. So let me take this mu n into 69 into 10 raised power minus 19 into 30 as common factor. So it would mean 2.5 minus VTH. It has to be multiplied with 0.07 minus of this quantity minus 1.5 minus VTH into 0.07. So from this we can see this is 65 minus this 25. Let us keep it as it is. So this will become mu n 69 into 10 to the power of minus 9 and 30, and this VTH and VTH will go because this is 2.5 into some number 0.07, and this is minus VTH into 0.07. Similarly, we will be having some number minus 1.5 into 0.07, and we will be having plus VTH into 0.07. So this VTH and this VTH will go, and we will be simply left with 2.5 minus 1.5 into 0.07, which is 0.07 itself. So let me write down it. Simply it will be 0.07. Now let us do the required calculations to get the mobility. Let us use the calculator. So it will simply be uh, divided by 30 divided by 69 divided by 0.07 into, it is coming out to be 0.276 into 10 to the power of 3 mu n. This is the mobility. So we can write it simply to be equal to mu n to be equal to 276. So let us check which value which match, whether it matches some value. Yes, it matches the value of C. So we have got the correct option, the C option. Let's write down the units as well. Centimeter square per volt second. So let's move towards another problem. It says that we have to use the constant voltage scaling for a MOSFET. This means that we have to, while scaling the device, we have to keep the voltage same. Uh, and the scaling factor in that case is 5. And as the MOSFET features are scaled down, what will happen to the current? So we have a list of the parameters over here. We can see this has been taken from some website. I think I have taken it from some website. And it says that when we have this constant voltage scaling, what happens to the parameters? Like the channel length will be scaled by 1 by k. In here, this alpha is scaling factor. So this channel length will be scaled by 1 by alpha. So we will be decreasing the channel length by this much amount. Substrate doping will need to be increased. That's what it is written over here. So there are some uh, implications of this thing. The implications are the current will be increased by this factor by which we are scaling. So since we are scaling the device by this what we can say, we are scaling it by this 5, so the current will increase by 5 times. So we will select this option. You can by yourself check these things as well. If you will write down these TOX parameters, like the parameters for the current, by writing the current equation. This, if we write down the ratio of the W by L, this W, this is the L and this is the W, so this W by L will remain as it is. For the mobility, you need to look into the things. And for COX, for a COX, you can see that when we divide this by TOX, that is epsilon ox by TOX, it will be 1 by alpha. It will be 1 divided by 1 by alpha. So this alpha will come in the uh, numerator, and this will be the multiplication factor of the current that we will be getting. Now there is another problem. It says that if there is some NMOS transistor which has the parameters, that is the channel length is 1 micrometer, the device width is 10 micrometer, oxide thickness is 25 nanometers, and the acceptor doping concentration is 5 into 10 to the power 15. And the voltage, the applied voltage are 3 volt. And there is some condition given that the device is to be scaled with constant field scaling. So it means if we have to use some scaling factor, so it means that if I'm scaling the voltage by 1 by alpha, I have to scale the length by 1 by alpha as well, so that electric field will remain the uh, constant. It will not be scaled. So this has to be constant field scaling. So this constant field scaling, in this, the there is some conditions, like in here what we have written, how the things will go. the channel length will need to be scaled by 1 by alpha, the voltage will need to be scaled by 1 by alpha. So we have been told to find the what would happen to the channel length and the uh, channel width. So simply we will be taking this channel length and dividing it by this scaling factor. This channel length is 1 micrometer, so this L nu will be 1 micrometer divided by 1.43. So I think it will be approximately 0.69. 1 divided by 1.43. Yes, it's 0.69. So let's write down this as zero point 0.7 micrometer. Similarly, for the width is given to be equal to 10 micrometer. So this new width new will simply be 10 micrometer divided by 1.43, which is 7 micrometer. So we will be having 0.7 micrometer and 7 micrometer. Now, what would happen to the TOX? We have to find for that as well. So for that, the oxide thickness that needs to be scaled by the same factor as well. So we will be scaling this oxide thickness. We had this to be equal to 25 nanometer. Yes, it was 25 nanometer. So it will be 25 divided by 1.43 nanometer. This is T ox nu. And let us divide this. It is 25 divided by 1.43. It is 17.48. 17.48 nanometers. So it is approximately equal to 17.5 nanometer. So we have completed this assignment. Let's move towards another assignment, which is the circuit part of this course. Mostly this is where the circuits will come in, and we will be having the small signal models to deal with. Now in here it
Hello,
say, huh? Yes, yes.
sir. From question number one.
Okay, okay. Question number one. This
Yeah.
assignment itself.
Yes, yes. This assignment.
Mhm. Yes. Lakshmi Kanta, please
Yes,
speak.
yes. Sir, actually, I have solved it in a different way. Actually, there was some parameter like GM is equal to mu on COX by L, VGS2 minus VGS1 into VDS. It was from the graph, that ID VGS graph.
For this question,
For this this question.
hmm
So from a graph, that GM is equal to mu1 cox. I'm not remembering well, but I have done it somewhere like that, like w into mu1 cox by L, VGS2 minus VGS1 into
hmm
VDS.
hmm
Since VDS is given
hmm
0.07, and somewhere it is like that I have solved. And
hmm
VGS2 minus VG1 VGS1 mu1 like that I have solved.
Is there any issue with that?
No, 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 sir. I have just linked it. From that also we can solve, or my process is wrong.
I don't know what question you are talking about. Maybe you can, if you want, you can share your screen.
No, no, sir. Actually, I'm telling how I have solved it. Actually, I have
Okay, no problem.
not
If you
not now. I have
if you
solved
have
it at least 1 week earlier.
uh, do you have any confusion in that
No, sir.
question?
No, sir. No, sir. No, sir.
Okay, then it's fine.
Okay.
If
Okay,
there is
sir. Okay.
confusion, you can ask.
Okay, sir.
Okay.
Another issue, sir.
Mm-hmm.
From NPTEL, from
Mm-hmm.
this week 10, 11,
Mm-hmm.
and 12.
Mm-hmm.
lecture slides are not available to download.
You can raise the issue with the NPTEL team. They will respond to you. You should write an email, or you can write in the discussion forum. If
Okay,
you
sir.
can write in the discussion forum, maybe the other TAs who are working on this slides thing, they will provide you with the lecture slides.
Okay, sir.
Hopefully
Okay, sir.
you can write it in the discussion form, or you can even mail the desired TAs what you have been told.
Okay, sir. Okay, sir.
Okay, I am not into the lecture slides. I'm sorry for that.
Okay, sir. Sorry,
Okay,
sir. Please
okay,
forward, sir. Go.
okay. So let's move towards the circuit part of this course. It says that we have some small signal. Actually, we have a MOSFET, and we can use this as a resistor as well. As we know in the circuit, if we have some circuit to build, we build the capacitors, we build the resistors, everything just from the MOSFET. We know that this MOSFET is having the capacitance associated with it. So we are building the elements of the circuit, like we are having some chips on the we are having some chips of the phone where we are having many transistors. So the capacitors will be built from the transistors, the MOSFETs itself. So in here we have been given a small signal resistance, and this is given by dvd by did. So this is the small signal resistance that is offered by this n-channel MOSFET, which is given over here, and this is biased at some voltage which is given to be equal to 2 volts. And we have been given the transconductance parameters, that is the mu and cox W by L, and it is to be given to be equal to 40 micro ampere per volt square, and the threshold voltage is given to be equal to 1 volt. And we have been told to neglect the body effect and the channel length modulation effect. So we will not be having or not in our small signal model. So if we can look into this MOSFET simply, it would appear to us this MOSFET is in saturation itself, because as we will see, this gate and drain, they both are connected, and source is here grounded. So VGS minus VTH will simply be some number which will be less than the VDS by the threshold voltage, as the G and D are same. So it means that this MOSFET is in saturation region. So if we now write down the MOSFET equation, I will simply try to say that this MOSFET is in saturation region by saying that since this is VB is equal to 2 volts, so VGS minus VTH will be equal to 2 minus 1 volt, and VDS is equal to 2 volts. Therefore, in saturation. So we have this MOSFET in saturation. Now let's write down the current equation in this saturation, which is ID equal to let's write down in the terms of this conduction this parameter, this transconductance parameter, sorry, this transconductance parameter, this is Kn by 2 VGS minus VTH whole square. So we were required to find this dVB by dID. We were required to find this dVB by dID, and this dVB is simply dVG by dID, or simply it is equal to 1 by dID by dVG, and this is simply equal to 1 by GM, that we all know. dID by dVG is GM. So let us do this simple manipulation, and since this source is grounded, this VGS will be VG. So it is simply this VGS We can derivate this. It will be dID by dVg. It will simply be equal to Kn times Vgs minus the Vth. That is all we will be having. Now, this is the GM value that we are having. This is the GM value that we are having, and this Kn is having the value of 40, I think. It is having the value of 40 micro, so it's 10 to the power of minus 6, and this VGS minus VTH was, I think, 1 volt. Yes, it is. VGS minus VTH is 2 minus 1 is 1 volt. So it is 40 micro uh, GM. Let this for this GM is 40 into 10 to the power of minus 6. Now this dVb by dId is simply equal to 1 by GM, or 1 by 40 into 10 to the power of minus 6, or 10 to the power of 6 by 40. So it would come out to be 1000 divided by 40. It will be 25, but let me recheck it. Okay, it's 25 into 10 to the power 3, which is 25 kilo ohms. So let's check the options. This should be in kilo ohms. Yes, the option should be in kilo ohms. So the option B is the one that we are going to select. Now we have another problem. It says that in this circuit we have been given some circuit in here, and this circuit we have to include the channel length modulation of all the transistors, and it has been told the channel length modulation is non-zero, and we have been told that all the transistors operate in the saturation have negligible body effect, so we can neglect the body effect. We have been told to find the small signal voltage gain, that is V naught by V in, and V naught is over this terminal. This is V naught. Now let us draw the small signal model. We can do it even without that, but let us draw the small signal model first. This small signal model, since we need to include this resistance effect, this channel length modulation, the resistance for that is given by 1 by lambda V ID, sorry, not VD, 1 by lambda ID. That is the resistance, that is the output resistance. So now we have to do the AC analysis. Let us see the circuit and let us draw this transistor first. Let us draw this transistor first. Let me draw this gate voltage. Its source is grounded. Absolutely. This is GM1, VGS1. This is VGS1. And this is equal to V in. We have been told that this is equal to V in. This is the small signal model for this transistor, and this is the its resistance, which is R naught 1. This is where we have to look into the voltage, the output voltage. This is V naught. Let us see the another transistor. Let me draw this M2 or M3 first. Let us draw this M2. This is its source. Okay, their source is connected. This source is connected to this, and this is this GM2. I think its name is 2. Yes, GM2, VGS2, and we will be having its R naught 2. Let us see how it's biased. This gate is biased with some fixed voltage, and we know this will be grounded during the small signal analysis. Since this is the fixed voltage, these have to be grounded. we have to ground this terminal, that is this gate terminal. It needs to be grounded. So we are grounding this terminal. This is the gate, and we have to ground this terminal, this drain terminal as well. So we are grounding these terminals. Now for the another MOSFET that is in this picture, we are having the gate to be grounded. This gate needs to be grounded as it is DC biased. So this will be having some bias, this gate bias. For example, let me ground this. So this is the gate bias, and this is let us be careful with this MOSFET. As you can see, this is not an NMOS, this is PMOS. So for PMOS, we know the source has to be at the highest bias. So this is the source and this is the drain of this M3. Let me write it like this: S3 and D3. So it means that its source is grounded, its source is grounded, and we will be having its drain to be equal to, so it will be like this will be gm3 vgs3, and its source is grounded over here, and we will be having another resistance which is r0 3. Simple. And these are connected to this drain. Now we know this is the VGS3, and it is this is the source, and this VGS3 is VG0, S is also 0, so this is 0. This means this will go. There will be no current source over here to act upon. So if we can see just by logical intuition, we have this R0 which is connected to this terminal and it is connected to the ground. It means that this R0 1 will be parallel to this R0 3. That is some logical intuition to this. But let us not go by that way, and let's try to do the current analysis. Let us write down the KCL for this circuit, and let's try to find out what we can obtain for this circuit. Uh, Let me write down, if I consider the current like this in this circuitry, this is the another current, this is another current, and this current comes in from this, and this is another current and goes in to this small signal model of this MOSFET 1. So it means I need to write down this KCL. So the KCL for this will simply look like, if this has been grounded and this is the V naught voltage, since this is also V naught, this will be V naught and this will be V naught, we will be having the current which is coming from this terminal. It will be 0 minus V naught by R naught 3, simply. And the current coming from this terminal, this and this terminal, will simply be equal to Gm times, this is VGS2, but VGS2, as we can see from this, this is the source of this MOSFET, which is M2. VGS2 is simply, VG is 0. This S is, as we can backtrack, this is V naught. This is minus V naught. So this VGS2 is minus V naught. So this is GM2 minus V naught. And over here, we will be having this current, which is another current. This current is 0 minus this V naught by R naught 2, and this has to be equal to, this current has to be equal to the current which is moving in this circuitry, which is GM1. This is GM1. VGS1 is V in. This is V in plus V naught minus 0, as this is grounded, V naught by R naught 1. So this is some simple manipulation that we have done, and we need to find out the V naught by V in this problem. Let's take the V naught on one side. So it will look like this. V naught will be 1 by R naught 1. Yes, 1 by R naught 1, 1 by R naught 2, 1 by R naught, uh, 1 by R naught 3 plus 1 by R naught 2 plus GM plus GM2. Okay, plus GM2 is equal to minus GM1 V in. So we know if we can use some simple manipulations, we know the parallel combination of the resistors. This is the parallel combination of the resistors uh, is given by, if we have some resistor R naught 1 which is in parallel with R naught 3, it will be simply equal to it will be simply equal to 1 by R naught 1 parallel 1 by R naught 3 will simply be given by 1 by R naught 1 plus 1 by R naught 3. This is simple. We are trying to get this in the form which looks similar to this. We could have, just by seeing the input impedance, is just written down the equations, but let us do the circuit analysis so that it it remains in our minds for a long. And this would mean this another quantity over here is the is 1 by GM2 parallel to R naught 2. So this quantity will remain, it will become 1 by R naught 1 parallel R naught 3 plus 1 by R naught 2 parallel 1 by GM 2, and this will be minus GM1 V in. So now these two are in parallel combinations. As we can clearly see, that's what we have been using the above. We have been using the how we can write the two resistors in parallel combination. It would mean that this is V naught by 1 by R naught 1 parallel to R naught 3 parallel to R naught 2 parallel to 1 by GM2. This will be minus GM1 V in. Now, since we required to find the V naught by V in, it will simply be equal to minus GM1 R naught 1 parallel to R naught 3 parallel to this R naught 2 parallel to 1 by GM2. So let us check the options. This is the gain. Let me write it as gain. So let us check the options. And 1 by GM2 is in, okay, it is in over here. This is what's here. Okay, this is the correct option to go with. So we have solved this circuit by using the small signal model.
So why,
No,
sir, M3's current source is
okay,
cancelled?
okay. You can you can see that this MOSFET is a PMOS, and for PMOS we will be having the source at the high bias as compared to the drain. So for PMOS, this is the source, this is the drain. Okay. For PMOS, we need to look into the VSG. That is what I have written over here. This is the, this has to be equal to where I have written. Okay, here. This is the VSG over here, this source to gate voltage over here, source is grounded, drain is sorry, gate is grounded. Where come from where come does it have the potential? It has no potential. There is no potential for this transistor, for this GM, because we know this current source is a dependent current source. It will depend on the biases that are there at the gate and source. Since gate is having the zero bias and the source is having the zero bias, it would mean that this current dependent current this dependent current source will go away because its VGS is zero. Okay.
But there will be a current flowing from R03.
Yes, yes, yes. That is what we have incorporated. This is that current. This is the current. This is the ground terminal that has been grounded due to the DC bias. This is zero current, and this is the current, and this terminal voltage over here will be V naught. That is the current we have written over here. This is 0 minus V naught by R naught 3. This current is moving. Had there been the transistor which had no output resistance associated with it, had it been such an ideal transistor, then we would have no current in this circuitry. But since we are having this channel length modulation, we are having this R naught 3, so we are having the current in the circuit. Okay.
Okay, sir.
So let's move towards the another problem. It says that we have this circuit in the figure and both are the NMOS transistors, and NMOS transistors are identical with the threshold voltage being 5 volts. Okay, we have to ignore the channel length modulation. Had this been the condition over there, we would have neglected that resistance, but in here we have been told that we have to neglect this channel length modulation only here in this case. So we can see this NMOS is in saturation. Let us write down this saturation current equations. If this is the current that is moving in this part, the same current should move in this part as well. That is some basic KCL we know. So if I write down the current equation for this MOSFET and say that this MOSFET is in saturation as well, so we need to verify this. So we will be having simply this current equation will be W by L for this MOSFET, 1 by 2 W by L mu n Cox. For this MOSFET is having this as gate and this as source. So this is the VGS will simply be equal to 30 since gate is connected to the drain. So this will be VGS 30 minus VTH, which is 5 volts, VGS minus VTH whole square. And this current has to be equal to the current which is moving in this terminal. So it is 1, it has to be equal to 1 by 2 W by L mu n Cox. Now VGS, VG, this is the gate, this is the source. So this VGS is simply equal to 10 volt. VGS is simply equal to 10 volt. Have we missed something? Yes, we have missed something. This is the VGS for this MOSFET. For this MOSFET, this is the VGS. So this VGS is equal to 30 minus V out. So we have written simply here, this is mistake. We have written simply here 30 minus 5, which is not the case. This is the gate voltage, this is the source voltage for this MOSFET. This means this is the VGS. We have to subtract it by VTH. This is VTH square. And this is for this MOSFET. We will be having VGS simply equal to 10 minus 0, as the source is grounded, it will be 10 volts, and VDS will simply be equal to V naught. So this is VGS minus VTH simply equal to 10 minus 5 equal to. So this thing will go, this thing will go, and we will be left with 20 minus 5 will simply be equal to 25. 30 minus 5 will simply be equal to 25 minus V naught whole square is equal to 5 square. So let's take the square root on both sides. It will be 25 minus V naught, and this will be 5, or V naught will be 20 volts simply. Okay. Now we have not taken the minus sign, and be careful about that, because that would have been the absurd result. It would have become minus 5, and when we have taken this minus 5 on the side, it would have given this V naught to be equal to 30 volts, which would have been absurd. How come a 30 volt supply would generate 30 volt voltage at its source? So that would have been the absurd thing to write down. And now let's move towards another problem. It says that we can see the circuit over here. This circuit is having some W by L, and uh, in here we have to ignore the channel length modulation, and we have to find this small signal gain in this case as well. So let's draw the small signal model for M1. This is the V in, this is the V in, and since the source is grounded, this will be GM1 times V in. We have to neglect the channel length modulation, so no resistance in parallel over here. So the gate is connected to drain. Since we are doing the small signal analysis, the gate will be connected to the ground. So this is the GM2 VGS2, and its drain is grounded. Okay, because drain or gate are connected, both are grounded. Now this VG is grounded, this is its source, and this is where we are looking at its output. This is V naught. So VGS2 will simply be equal to 0 minus V naught, or minus of V naught. So we can, from this we can see there is only one current which is going into this current. So GM2 times VGS2. VGS2 is nothing but minus V naught. Minus V naught is simply equal to GM1 times V in. Okay, so it would mean this V naught by V in is equal to minus GM1 by GM2. Now we have to be careful over here. Since the current is constant in this circuitry, the current is moving, we need to get this in some factors which is having current as a common factor, so that we can cancel out that current prefactor. We know if we have some MOSFET which is in saturation, this its current equation will simply be given by ID equal to 1 by 2, wait a second, W by L mu n C ox VGS minus VTH square. From this, I can write down this VGS minus VTH to be equal to 2 times this ID divided by W by L mu n Cox under root. So let me name this equation as equation 1. Now for this GM thing, we know GM is equal to dID by dVG. Since we got this as the ratio of two GMs, I need to find the GM. So GM is dID by dVG. So it will simply be equal to, if I derivate this thing, it will simply be equal to W by L mu n C ox VGS minus VTH. Now let me multiply this thing by 2 and divide by 2 and multiply it by, let me do this thing, VGS minus VTH. If I divide by this thing VGS minus VTH, I have to multiply as well, this will be mu n C ox. This will be VGS minus VTH whole square. If we can see, this VGS minus VTH will go with this VGS minus VTH, and we will be left with just with the VGS minus VTH. 2 and 2 will also go, and we will just be left with this W by L mu and Cox VGS minus VTH. So these are same expressions. Now in here I can simply say this is equal to ID, so it will become 2 times ID by VGS minus VTH. Okay, this is 2 times ID by VGS minus VTH. Now I know what is the value of this VGS minus VTH. It is this value. So I will divide by this value. It is 2 by ID divided by 2 by ID divided by W by L mu and Cox. Okay. Let me use another slide. So this 2 by root ID will go with this 2 by root ID. It will be just the this GM will be equal to root 2 ID mu n C ox W by N. So this will be the GM. Now we got the ratio of this output to input voltage, that is the gain, to be equal to minus Gm1 by Gm2. So we have this V0 by Vin to be equal to minus Gm1 by Gm2. Let me write down the Gm1. Gm1 will simply be equal to 2 times ID. We did this because we knew that the current is same. This is mu n Cox. This will be W by W1 by L1. Similarly, this will be for GM2 2ID mu n Cox W by L2. From this, we can say that this 2 and ID, mu n and Cox will go, and we will just be left with W by L of transistor, sorry. So we will be left with W by L of this transistor 1 divided by W by L of transistor 2, its square root. This is minus times this thing. This has to be minus times. So let me check the values. It is 40 by 0.5 and 10 by 0.5. So it is 40 by 0.5 and 10 by 0.5. Let me write down as this will be 40 by 0.5 and 10 by 0.5. It will be simply equal to minus 4 under root, or it will be equal to minus 2. So gain is equal to minus 2. Let us check the options. We have got option B as the correct option. So we have got this correct. This
So,
is
so its gain does not require mu on Cox. Doesn't
yes,
depend.
yes, it
It's a
does.
nice circuit.
You can say that. But at the end, it will depend. So now, okay, let's move to this fifth problem. It says that we have to consider the following circuit, and the threshold voltages of these is, but Lakshmikanta, it depends on the W by Ls. From where can we get these W by Ls?
Yes, sir. Yes.
Uh, you have to be careful with those as well. So it says that we have some MOSFET which is given over here with the both are in saturation. We have to neglect the channel length modulation, and we can write down the current equations for both the MOSFETs by simply, we know the current equation for MOSFETs. We will simply write down, we know the current in this MOSFET will be moving in this MOSFET as well. Both are in saturation, and from the KCL we know this has to be equal to both the currents. This is W by L. This is mu n Cox. And for this, we are having, for this MOSFET, we are having VGS to be equal to 3.5, and here we are having 1.5. This means that we are having 3.5 minus 1.5 as VGS, and VTH is minus 1.2. So this is the VGS minus VTH. Okay, we have to find the W by L. Okay, find the W if L are same. Okay, let me write down this as 2 and this as 1. This has to be equal to 1 by 2 W by L of 1, this transistor 1, mu n Cox, and this is VGS. VGS is 1.5 minus 0. Okay, it is VGS is 1.5 minus 0 and VTH is 1.2. So from this we can cancel these terms. We can cancel these terms. It's fine. So it becomes W2 by L2 is equal to 3.5 minus 1.5 is 2. 2 minus uh, 1.2 is zero point 0.8, so it becomes zero point 0.8 whole square, and this is squared as well, so it becomes W1 by L1 zero point 0.3 whole square. So this L1 and L2 will go since both are equal. Okay, so this W1 by W2, W1 by W2 will simply be equal to what we can say, it will simply be equal to zero point 0.8 square by zero point 0.3 square. Okay, let's use these calculator to calculate these values. So it is equal to zero point 0.8 into zero point 0.8 divided by zero point 0.3 by zero point 0.3. So it comes to be equal to, wait a second, there is some mistake, zero point 0.8 into zero point 0.8 divided by zero point 3, okay, divided by zero point 0.3. I divided it two times. Okay, it is 7.11. This is the W1 by W2. And if we check the options, it is option A. Now let's move towards another problem. It says that in this circuit, which is in this figure, we have to find out the what we can say, the threshold voltage of the MOSFET is given to be equal to 0.5, and this input voltage V in over here is given to be equal to 1 volt, and this DC output voltage is given to be equal to 1.5 volts. This is going to be equal to 1.5 volts. We have been told to assume this mu n Cox to be equal to 0.1 uh, um, zero point 0.1 mega, and we have been told to take the channel length modulation factor to be equal to zero point 0.09 per volt. From this, we have to find out the current through the MOSFET. We have to find out the current through the MOSFET. Let us use the simple, what we can say, KCL. Let's use simple KCL. Current in this will be current in this and plus this. So if I write down this KCL, it will simply be this voltage over here is V naught is 1.5 volts. So it will simply be equal to this VD is equal to 3 minus 1.5 divided by 10 will be the current in this. This is 10K is equal to the current in this circuit. The current in this circuit is simply 1.5 minus V in. V in is 1 volt divided by this. This resistance is 10K. So this is 10K plus the current in this. Let us denote the current through this MOSFET as ID. So this will be 3 minus 1.5 will simply be equal to what we can say, this is equal to 1.5 and this is equal to zero point 0.5. So it is equal to 1.5 divided by 10 milliamperes minus of zero point 0.5 divided by 10 milliamperes is the ID, or simply we can write this equal to 1.5 minus zero point 0.5 will be 1. 1 by 10 will be zero point 0.1. It will be zero point 0.1 milliamperes. This will be our ID. So ID is equal to zero point 0.1 milliamperes. So I think it's already 6, and this is all that I had. Uh, and mostly after that we have I think there are some questions which are related to the W by L's, and there are some theory questions, one or two, and we know that the MOSFET is generally biased in the saturation. This is all we know. And similarly, this is also a known fact that whenever we study, we say that this MOSFET is a voltage control device, and it has to be having high input impedance. So it is voltage control device with high input impedance. Similarly, this effective channel length of a MOSFET in saturation decreases with the drain voltage. That's what is the channel length modulation that we have studied. Now we are left with just this problem. It says that we have to, with respect to given details given in question 6, we have to find a W by L. This W by L, we know this current is equal to zero point 0.1 milliamperes. This current is equal to zero point 0.1 milliamperes, and W by L needs to be find it. This is we need to find this W by L. This W by L will be equal to mu n C ox, mu n C ox, and VGS minus VTH. So VGS minus VTH needs to be looked into. VGS is simply this voltage, which is 1 minus this thing 0, and we have to subtract it by VTH. VTH is 0.5, so it will become 1 VGS minus VTH will simply become, wait a second, so it is VGS minus VTH. Okay, it would simply become 1 minus zero point 0.5 whole square, plus we have to take this channel length modulation into account, 1 plus lambda VDS. This is 1 by 2 W by L. Mu and Cox, I think it was given to be equal to zero point 0.1 into 10 raised power minus 3. So it is 0.1 into 10 raised power minus 3, and this is equal to zero point 0.5 whole square. And this 1 plus lambda VDS, lambda is given to be equal to lambda is going to be equal to 0.09, and VDS is going to be equal to 1.5. VD is over here and source is grounded, so it is 0.09 into this 1.5. So if we solve this, we should get the W by L. So we just need to solve this equation to get the value for W by L. Okay. So I think this is all I had in this assignment as well. So if we have some questions we can take, or else we can end this today's session.
No, sir.
Okay, thank you Lakshmikanta. So thank you
Uh,
for joining the session.
Sir, all your slides are available in Google Drive. Okay, sir.
Yes, I will upload this one as well.
Okay, sir. Okay, sir. Exam is coming nearer, na? That's why.
Okay, I will upload this just right away.
Okay, sir.
Okay,
We have
fine.
another session, sir. मतलब assignment 12.
I don't think so. There will be another session.
Okay, sir. Okay, sir.
I don't think so.
So this is the last session.
Most probably this is the last session. Yes.
Okay, sir. Okay, sir. So,
Thank. Okay.
sir, any tips and tricks about the exam, or
Hmm.
actually I'm giving first NPTEL exam this month.
I just prepare well. Prepare as the professor, as we know that professor has taught this course really well. So Just revise everything what he has taught. Get the basics right. You will fare very well in the examination. Just
Okay, sir.
do the things from the right from the basics.
Okay, sir. Sir,
Okay.
actually, I want to ask you that what are your matlab, description? What are you working on research?
I can't discuss this over here. I'm sorry.
Okay, sir.
I'm sorry.
Actually, matlab, madam also other NPTEL they are telling what their research are doing. Actually, what is the domain actually? Matlab,
I work on 2D materials.
2D material. That is also I'm asking, sir. 2D materials. Okay, 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 sir. Okay, sir.
Ah, thank you.
Thank you, sir. Thank you. Thank you for the session, sir. Thank you.
Thank you, Lakshmi.